going to be looking at the position and momentum stuff a bit more in detail. And let's just get going. So it's probably going to be a short. Um, it's probably going to be a short session today. Mm, but we'll see. I just basically not to lose track of what I was doing last time. It was about position and momentum wave function. And so it was about the derivation. I wanted to at least start taking a look at the derivation. So a three-dimensional wave function in momentum space can be expressed as a weighted sum of orthogonal basis functions. This is what I want to take a look at it. So essentially what it is saying is it's fairly simple. It's just saying, you know, if I have let's try to I think there's like a paint thing, right? Paint online. Chase paint. There you go. So, you know, it's like let's imagine, you know, this is my oh, I can use my fingers. This is my basis, and I have, you know, I have these vector in here. Maybe I'll just change color to something red. So I have this vector here. And now let's say, you know, this is position, and now I wanna go to the blue one, which is momentum. And let's say that I'm saying, well, you know, this is a position vector, so I can, you know, I can express it as let's say there's another base, and I'm not gonna even draw it like um, I'm not even gonna draw it perpendicular to orthogonal to the original base, which would be these, by the way. So it's, oh, I think it's too thick. So let's say this is the basis, yeah. So below. So now basically I have sort of these, you know, there's this component here, this component here. So, you know, let's say this is px and this is py, right? So um, you know, well, essentially, this is the same as just saying py times sort of the y basis, whatever that is, right? It's just, this is y and this is x from a p perspective, yp xp, right? Plus my favorite. This is awful. Anyway, px xp. Like that's the point, right? So these would be the basis vectors. So this is what we're saying is like in, and that is these in momentum space. That's all this is saying. It's like you can always just express it as in some other um, basis. That's all this is saying. So okay, orthogonal basis functions. This is kind of like converse a three-dimensional space can be expressed as a weighted sum of orthogonal basis functions. Mm. Yeah, I'm assuming I'm intuitively you can exchange those values by functions, and so that's what you're getting here, um, or as an integral. Mm. Now, why would you do an integral? You do an integral when you're why would you do an integral though? Would you do an integral because it's a very big space? I'm not so sure I understand this step. And then the position operator. Okay, so essentially the position operator is what takes observable of a particle. So what we're saying with the position operator is the operator that corresponds to the position observable of a particle. When the position operator is considered with a wide north domain, then the space of the tempered. Yeah, okay, guys, give me a second. So its eigenvalues are the possible position vectors of a particle. Let's see these. So in quantum mechanics, the position operator is the operator that corresponds to the position observable of a particle. When the position operator is considered with a wide and north domain, the space of tempered distributions, its eigenvalues are the possible position vectors of the particle. In one dimension, we denote the unitary eigenvector. In one dimension, if by the symbol we denote the unitary eigenvector of the position operator corresponding to the eigenvalue x, and x represents the state of the particle in which we know with certainty to find the particle itself in position x. Therefore, denoting the position operator with the symbol x, in the literature we find also other symbols for the position operator, for instance q from Lagrangian mechanics, x and so on. We can write for every real position x. One possible realization of the unitary state with position x is the direct delta function distribution centered in the position x, denoted by delta this dx. So quantum mechanics, the ordered continuous assembly of all the functions is called unitary position basis in one dimension, just because it is unitary eigenbasis position. Even though it's fast, no idea what that means. Whatever that means. Basic properties, eigenstates, 3 dimensions. So the generalization to 3 dimensions is straightforward. Let's start from the eigenstates. Basic properties. Basic properties, no eigenstates. The eigenfunctions of the position operator on the space of terms represented within space. Informal proof. Okay, so this is just a proof that they should be delta distributions, the eigenfunctions. It means that they are just like, it's like a big spike. Metal bases. What does the position operator do when you multiply it to a system? It basically tells you the probabilities that it will be, and that, you know, in not that, but like the expectation value, or yeah, squared will tell you the probabilities of the different positions, and if not, how to understand sort of the position operator, the position operator. This is something that is just hard for me to have like a mental model for. What is the position operator? Is the operator that corresponds to the position observable of a particle. When the position operator is considered with, okay, that's what I just read. How do you use it? Position are operators. How the position operator and the position bases are correctly defined. In quantum mechanics, if one deals with wave functions, the Hilbert space in question is for a particle in a dimension, the position operator corresponds to the ith coordinate is exactly defined by whatever that is. Now, if we generalize things slightly, we have a state space, which is a Hilbert space with state vectors describe its possible states of a system. In this case, the position operator is usually defined by, okay. But here's the problem. This definition depends on a particular basis. But how those cases are defined? Well, they're defined exactly as eigenvectors of the position operator. So to define the position operator, we need it in a certain basis. But to define the vectors of that basis, we define then as the eigenvectors of the position operator. This is circular. So what is the accept? Is there any accepted answer? No, but this one has a lot of upvotes. In quantum mechanics, the position operator and the Hilbert space are defined contextually. The Hilbert space and the operator position along xk is defined in that space with the obvious domain. You can adopt a more abstract viewpoint if you simultaneously define the momentum and the position operator satisfying CCR, whatever that is. In that case, one assumes that there is a continuous basis. That's why you do an integral. There's a continuous basis. I know like that continuous basis existed. But this is even, what's even the formal definition? Continuous basis mathematics. So it's like if you think about one, well, I mean operators, I understand operators as it's a function over a space of physical states into another space of physical states. An operator is basically a function that helps you go from one, it transforms a state into another state. So how is position operator? Okay, so position operator is basically an operator that tells you like how is the position evolving, right? Okay, yeah, that makes sense. So it encodes that. It's how is the how is that evolving? Yeah, yeah. But then what is the meaning of the eigen functions of that operator? Because these are then functions where the eigenfunctions of the position operator. What is the interpretation of that, of the eigenfunctions? Do they correspond to the basis? Like what is the, so this is all supposed to be the eigenfunctions, and then what we're doing is, I get it why it's an integral, because it's a continuous basis. Okay, this makes sense. I'm not so sure what the D3 means in here. But okay. But essentially it's like, as a version of these, it's like the specific, okay, I think in a way what this is doing is saying, is actually decomposing the operator. Could that be? It's like saying, it's like saying, take that eigenfunction and multiply it by, so this is your starting point. This is your starting point. It's basically the wave function in position space. And so what we're doing is we're multiplying each of the so you're taking your eigenfunctions of the position operator, not the position, but this should be the momentum operator, right? I don't get it. Or not. So you're saying, so you're defining the, we're defining here the momentum operator, and we're defining it as the integral. So what we're doing is we're saying, well, if we take what the position operator is doing is evolving the okay, so it's evolving that. So you're saying take the eigenfunctions, but these are the eigenfunctions of the position operator. Keep multiplying and adding them or integrating them. And then and that's it, and that gives you the momentum. That is what's a bit odd. First of all, why are we multiplying the eigenfunctions by the actual wave function in position space, and why is this giving us the momentum space? I don't see the intuition. I would assume, yeah, the position operator. So, and that's the momentum space. Why? A three-dimensional wave function in momentum space can be expressed as a weighted sum of orthogonal basis functions. I just don't get why this gives us the momentum wave function. Maybe I just need to see some concrete examples. of these. But okay, there's two things. So one single example, another thing, understanding what the eigenfunctions are then. So the eigenstates of the position operator are delta functions. To each observable in quantum mechanics is an operator corresponding to it. I don't understand what's the meaning of the eigenvalues of the X operator. Since X is Hermitian, eigenvalues correspond to real numbers. What's their physical meaning? If they describe the particle localized at a particular point, blah, 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 blah. If these momentum operators do not commute, the eigenvectors of the Hamiltonian are usually different from the eigenvectors of both position momentum operators, but I see in books applying the Otto states of the Hamiltonian operator. How do you find such? Okay. Eigenvalues are the values that are measured in the experiment, are the values of the position obtained when measuring it. Every measurement will produce a different result, different eigenvalues, unless the system was prepared in an eigenstate of measured quantities. Okay, yeah. Question statistics. The state of the system does not have to be an eigenstate of all the operators, which is pretty much the point of the uncertainty principle. There's an eigenstate of I still don't get it. What the meaning is. Because we choose to work in the basis of eigenvectors of x, wave functions. We have a Hilbert space, which is a vector space in which we can choose any basis we wish. We mustn't choose to work in a basis that diagonalizes the position operator. Why? Once it is chosen in a state. Momentum operators in coordinate bases. Okay, so you might ask, how can one derive the expression of the momentum operator P in the coordinate basis? This is done as follows. The fuck? By definition? What? I don't get it. I don't get this. What I don't get is intuitively why why. So I don't get why. This is where I'm stuck at the moment. Why does these? Why does this? Why doing these leads to the momentum? It just doesn't make sense. These basis functions, these orthogonal basis functions, we're actually just what we're doing is we're taking the eigenfunctions of the position operator. So essentially, what you're doing is and then you're integrating over that. I think that's the point. The point is you're integrating. The trick is somehow in the fucking integration. Um, and again, I just have no idea what this D3 here is. Convert to momentum space. Momentum space wave functions. Okay, so maybe this is explained here a bit better. In free space, we said that the time-independent Schrodinger equation is the following, which has a solution, blah, blah, blah. So this is in free space. Cool, we know that. For a wave traveling from left to right, left to right, both with energy, blah, blah. So we could, in fact, simplify this a bit with, okay, adding this k, plus, minus, and then just doing this. This is a particular solution for any direction. We get more physical insight into this by writing the momentum operator. Okay, so we get more physical insight into these by running the momentum operator as an eigenvalue equation. So you're doing basically, okay, so you're actually just doing an equation and then deriving it from that. That's so you're saying, okay, so you're saying the derivative, what is f of x? Where's that even? I hate that, like, Jesus. I guess it's just whatever. God. So plane waves, which are eigenfunctions of the energy operator for free space, are also eigenfunctions of the momentum operator. So these conserve momentum. So I have a well-defined determinants of momentum. So there is some sense in which this is not a physically realizable state. To normalize it, we need determinate momentum. Fourier transforms. Whatever, that doesn't help. That didn't help. So let's say I have a state vector in a position space with an orthonormal position basis. If I now use an operator P on these bases, okay, so that actually that's the first that's a question that I have as well. Like, what happens if I use the operator, the momentum operator? If I now use an operator P on these bases, I will get the basis which corresponds to a momentum space, and projections of on these basis vectors will now be. No, I don't think so. That's the point. I don't think that's true. You can't. So what will you do if you what will happen if you apply a momentum operator to a wave function that is in position space? Or maybe that's the whole point of the equation, is to say that if you evolve somehow, if you were evolving no, the wave function vector is supposed to be a function of time only. When you write t, you're not considering the projection of the function nor the position neither in the random space, but just to say that the system at time t, which is nothing but a postulate of quantum mechanics. Will have the wave function. You will have the wave function in coordinate or momentum or any other observable once you project your state vector on the basis of the observable you have chosen. For instance, in coordinate space, then you do these. Oh, my headset is running out of battery, so I might actually, my sound might just go. Oh, sorry, I actually had missed the chat because I only have one screen. You integrate out all the R's and you get the wave function in K space. Yeah, that's kind of what I think. So D3 is all space. So everywhere the relevant wave function reaches needs to be included. There's a known. There's a space derivative. Yeah, of course it is. Yeah, of course, this is a derivative. I mean, this seems intuitive that it's a derivative. And applying p hat will take the derivative of the R space expression. I'm not so sure I understand all that. So, but thanks for the hints. Sorry, because I'm just working on one screen these for the coming week. So I for some reason I just can't see the chat unless maybe I should be able to pop out the chat in the screen somehow. Can I pop out the chat? Show viewers list? No. I have to think whether I have to see if I can pop out the chat and at least have it floating on my screen, because then I can at least talk to you guys. So thanks a lot. Yeah. That's just, exploring here stuff and just trying to learn stuff on the go. But I mean, yeah. Actually, that's probably the best thing to do. I mean, I'm then putting all the videos in YouTube, so I will come back to that and then take a look at the chat. Yeah, I think the struggle is always what matters. And anyway, I'm just probably running out of time anyway. I'm going for half an hour now, and I don't have so much more time today, sadly. But let's just go through these. So the wave function, yeah, okay, so get that. Kind of okay. This is still, I keep struggling with these, and again, as I said, my headset keeps informing me the sound is going to go off in a bit. So apologies if that goes on mute. Maybe it might actually switch to the computer speakers. We'll see. But then it's going to be really loud because they're really shitty. Whatever. Let's assume that's okay. I'm not really agile. Not agile. I'm not really well educated on these. I feel like, yeah, I get it. The wave function. Okay, but it's a vector. Yeah. Okay. Sorry. I keep getting confused. The wave function does typically, oh, let's say just we have this. Okay, let's ignore the cats and stuff for now. The probability amplitude of if you want to switch from coordinate space to momentum space, you want to have the following probability amplitude. Okay, yeah, I get it. I mean, I get it in the sense that what this is just telling me is this is just a projection. That's what you're doing is a projection. But I'm trying to understand this without the vector notation. So I will see. I think I have to wrap up now. For each t having inserted the completeness relation, the space observer now knowing you'll find that the projection of wave function in momentum space is the Fourier transform of the coordinate space. That doesn't satisfy it doesn't answer my question. I feel that it's just a way to say, well, just do the projection. Assume you know these, just do the projection, and then that's not what I was looking for. I was looking for something a bit more intuitive at this level. Like I have. Yeah, I know. I mean, there is a derivative relationship between position and momentum. That's for sure. It's an obvious one, classically speaking. Okay, so you're just saying that's just the integral because it's the derivative of momentum. Yeah, maybe that's just the most intuitive way to understand that, and probably that's what you're saying, right? Um, in R space, the momentum operator is a space derivative. So you're integrating, to recover that. When I do electron modeling calculations, I write the wave functions as space functions, like those chemistry orbitals. That goes definitely. I take the operation of those functions. That goes definitely way above my pay grade at the moment. But yeah, thanks for the insight in there. Let me see. Yeah, I have to probably wrap it up here. Um, I don't think I have cleared anything specifically in this session, but I will eventually. I have to sleep on it. It just that's what's bugging me a bit. But it might just be that it's just mm, maybe I'm trying to understand something that does not really need that level of intuition. I don't know. Yeah, yeah. It's definitely struggling to find a bit longer periods of time to actually focus a bit more because like 30 minutes, 40 minutes is not enough sometimes, or most of the times. But we'll see. Better than nothing. Cool. Yeah, I'll wrap it up and just basically do another session as soon as I can in the next couple of days. Thank you.